Introduction to Microprocessors and Embedded Systems Development, Lecture 1. Hello, everyone. In this lecture, I'll start talking about microprocessors and embedded systems development. Now, in order to understand embedded systems, we have to understand microprocessors and microcontrollers. Why do we use them? How do we use them? So, before we get into the details, the references that we are using, the lecture notes, the main textbooks and auxiliary books, they're all found in the first slide in the lecture notes. So the textbook, chapter 1, will be covered in this lecture. So here is the outline. We'll start with the goals and the tools that we are going to use in this course. Definitions related with the microprocessors and the microcontrollers and also embedded systems. We'll also talk about and give an example of a system, and then we'll get into the computing. What are the fundamental blocks that we are using in computing, like CPU, memory types, buses, and one of the major cycle that we call it fetch, decode, execute cycle we use in CPUs, and two types of architectures that we are going to talk about. So the course goal is to understand the fundamentals of microprocessors. Why do we use them? How do we use them? Why are they so useful and so on? And how we can interact with the outside world with these devices. So hardware interfacing and system design techniques are important topics over here. We'll also learn assembly programming because high-level languages that you can use in everyday life, it's easier and it's easy to understand, easy to write, and so on. Assembly, it's more machine language related programming language, and we have to understand assembly as well, how instructions are encoded and decoded into programming languages, and how we can use this hardware interfacing with a selected microcontroller so that we can easily understand the embedded system design on any architecture. So prerequisites, logic design, and any programming or hardware design experience will also be helpful. So generally the topics, microcontroller basics, hardware organization, what do we have inside of it, the type of instruction set, how do we execute these instructions, programming basics, simple assembly instructions, and also high-level instructions, how we interact with outside, I/O interfaces, buses, memory accesses, digital analog interfaces, and so on. Common peripheral devices like memory switches, LEDs, keyboards, motor sensors. These are all going to be used in embedded systems, so we have to know how we can use these devices or the resources inside of a microcontroller so that we can interact with these devices and also interrupts. So the learning tools, we are focused on AVR Atmega 128, which is an 8-bit microcontroller in this course. And in order to write an assembly code, we are using Atmel Studio, integrated development environment, which you can easily download that. And system design and simulation, Protos, and system prototyping. We also have development boards with Microboard for AVR. And also, you can find different types of C compilers which could be useful in order to develop any embedded system. So, if we get into it, what is the main difference? What do you know about microprocessors or microcontrollers? What are the main differences of these two types of products? Some people are thinking that they are the same thing. They are actually similar things, but they are not exactly the same. So microprocessors is a general purpose, not really specialized, and it's a one chip controlling element. We call it the brain of a computer system, and it can perform three main tasks. the data transfer between memory or I/O system and itself, arithmetic and logical operations, and control the program flow, decision making based on the conditions. On the other hand, we have got microcontrollers. So microcontrollers is not a general purpose. So they're specialized. We are using for specific applications or specific programs. So that's why we use them in embedded systems a lot. So you can think it as a small scale processor, and they have a different desirable characteristics which you can pick up and use it. And we have to be careful while designing our embedded system. There are a couple of design metrics that we need to take care, like the cost, system integration, which we call it size, power consumption. These are all important in low-level system design. Okay, so what do we know about embedded systems? They're specific. They're specific systems that we use for applications. Okay, they can be found in the car ABS system. They can be found in the planes. They can be found in the televisions or maybe medical monitors and so on. So, for example, in the early days, mobile phones were also embedded systems uh, type of devices. But nowadays they changed into the general purpose systems because they're not just serving simple texting or calling, they can do any kind of multitask processing and information delivery. Okay, so let's start with the systems, how we analyze it, how we think about as a system. Now, in general, when we talk about the systems, we have got some inputs coming from outside. It can be any kind of input, analog or digital inputs. Now, these inputs are getting into something which they are going to be affected, and they can do some operations in there, transformations or something like that, and it will produce some outputs based on that calculations. And in the end, we end up with some outputs, which will be useful for something else, or which will be useful to control something. Now, what do we mean by embedded systems? We have got small computations, we have got small devices or actuators that all of them are working in harmony and creating specific tasks. By this means, rather than using general purpose systems or processors, we can easily use embedded systems, which is going to be a low cost, smaller size, but it can serve the functionality required. So here is the formal definition of an embedded system. It's a special purpose computer dedicated to a particular tasks, like an ABS or cruise control systems in automobiles, power electronic controllers, robotics, and so on. They are low-cost microcontrollers, which they are not complex. They have a small storage like memories or small disks compared to the general purpose devices. And they have got the fewer and task-oriented peripherals. So we are just using a couple of sensors to get some measurements, for example, and maybe a couple of switches or LEDs over there in order to show the outputs and so on. Now, when we are designing embedded systems, we'll do modeling. Now, these are, as I said, as they are working in harmony, they're actually going in and out from each other. So, three main objectives: modeling, design, and analysis. Now, modeling, we have to model the system before we design it. We have to understand, okay? So, we have to understand what this system is going to do. Okay, so we have to model it, we have to imitate it exactly how it is going to work and what it's going to do. And then we have to do a design. Now, design is important in electronics because it has to be structured and it has to be carefully crafted so that we can have and we can show how the system is going to work. Okay, so what and how. And then once we have got the design, we had to do some analysis. So we had to do analysis to show a deeper understanding how the system is working, and it will specify why a system does what it does. Okay, so these are working all together to have a perfect system. For example, quadrature aircraft. Now, when we think about modeling, we can model the flight dynamics, modes of operations. Different modes can be transitioned through each other, composition of behaviors, and multi-vehicle interactions. Now, when we think about the design, processor design, memory system design, sensor interfacing, concurrent software, these are all affecting the system itself. So, what we are modeling, how we are modeling, and now why. So, specifying safe behavior, achieving safe behavior, verifying safe behavior, and guaranteeing timelines. Now, these are all together. So, if we get into the details of this quadrotor aircraft, you can see that there are lots of different resources over here, like Pentium mobile processor, RAMs, Stargates, and Atmega 128, some trackers, SRS, Superstar GPS, and so on. Now, this is not what we are going to get into, but as this is an introductory course, you will have an idea of how these type of systems are going to be designed. Okay, so this is going to be a brief overview of what complicated system does, but we are going to do some simple or maybe some similar system designs like these. Okay, so now we understand what microcontroller and microprocessor is. We understand what embedded systems and the general purpose systems differences are. And now let's get into the computing because we have to understand the computing or the internal organization of the computers in order to understand these systems. So probably you all know this, but it's just going to be a simple revision of it. Now, there are different parts of the computer, IOs, inputs, outputs that we are interacting with the outside world, keyboard, mouses, sensors, actuators, printers, LCDs, LEDs, and so on. Memory is another block, which we want to keep the data in, store it. CPU is one of the fundamental devices in computers which performs arithmetic and logical operations and connecting the different parts. So CPU can be connected to memories, CPUs can be connected to IOs, and everything is controlled by the CPUs. So we need to understand how computers work in order to understand how microprocessors or microcontroller based systems work. And this is what we are going to do in this first chapter. Okay, now, if we start with the typical organization of a computer, what will be the first diagram that we can draw? Now, for the first diagram for the computer organization, we need few basic blocks. As we already mentioned, CPU, which we know it as a central processing unit, should be in the center. Okay, and inside of this, we have got arithmetic logic unit, which performs arithmetic and logical operations like you have seen in logic design. And we also have some control units over here, which controls the operation. Okay, so they are interacting. Now, CPU are also talking with the memory in order to store and retrieve data from it. And on the other side, it's interacting with outside world with IOs. Okay, so this is a typical computer organization. Now, so as I already mentioned, arithmetic unit executes arithmetic and logical operations, add, shift, and, or, that we all seen all these in logic design. Central processing unit is the combination of the control logic, which controls how the data is going to be stored, where to be stored, retrieve the data, and so on. And which is actually the brain of the computer. Now, on the other side, when these are all working together, okay, now we have got some buses inside of a computer. Now, what are these buses? We have got data bus, we have got address bus, and also we have got control bus. Let's change the color. Okay, three buses that they are going through the system. Now, on the other side, we have got our devices or the logic blocks like CPU, like memory, and of course, I/O. Now, one thing that we need to be really careful, which of these buses are going in and out from which part of these logic blocks. So if we consider data bus, when you think about the data bus, is data going into the CPU? Yes. Is data coming out from CPU? Yes. Think about it as an arithmetic operation. You get the data into the CPU, 3 plus 2, 5. You get the data out from the CPU. So that means data over here is going to be two-way. And if you think about the memory, you store the value over there, you get the value from that, and then you process it in the CPU. So it's two-way. And of course, I/O, getting a data from a sensor outside or sending it to an LED, that also has to be two-way communication. So the data bus carries data stored in memory or an I/O device to the CPU or from CPU to memory or to an I/O device. Then address bus. Now, when we think about an address bus, where does the address coming from? So address is actually the memory address, or it's actually going to be the I/O address. So who is the boss over here? Boss is the CPU, the brain of the computer. So the bus, address bus, the CPU has got the control, so it's sending out the address. Memory is receiving the address. I/O is receiving the address because each of these I/O places or memory places, they have got their own specific address that we want to retrieve or send out the data. So carries the address of a unique memory or in and output, input output device. So it's one way. Now, the other one is the control bus. Now, when we consider control bus, who is the boss again? CPU is the boss, but we can also get some control outputs from the memories as well. CPU is sending these control info, but also retrieving some feedback back as well in order to synchronize the whole system. So it's also two-way communication. Okay, so this is important. We have to know how these buses are operating through the computer organization or inside of a computer. Okay, then. Now, this is a typical computer system, and we have seen three resources, memory, CPU, and I/O, and we have seen how they are interacting with three different buses. And this can also be seen from these figures over here with more details on it. Next, what we are going to consider is a typical microcontroller system. So what is a typical microcontroller system? I can directly show it from the block diagram over here. Now we have got a microcontroller, a chip in an embedded system. There's a power supply, converters, memory, peripherals, clock generators, and buffers. So let's get into one of these and one by one explain how these are affecting the whole system. Now, power supply is a typical power supply which converts incoming 220 volts into 12 volts or maybe a 5 volt DC because these types of systems are working with a low voltage. This is really important in embedded system. We won't get any higher voltages. And microcontrollers generally operate with 5 volts. So we also need converters, which they are typically a DC to DC conversion to obtain the various voltages like 1.5, 2 volts, which is required by the rest of the system. And then we have got the clock generator. So clock generator, it generates the clock and supplies to all devices so that they will be synchronous, and when the clock is changing, data is changing. Okay, this is easy to design a system with a clock. And the control signals, so like we said, microcontroller, and inside of a microcontroller, CPU is the boss of the system, the brain of the system, which actually tells when to receive data, from where and how, and what to do with that data. So they have to be coordinated, and these are all done by the control signals. Okay, and data signals, once we have got data maybe processed or maybe received from outside, we have to process that data and store it in maybe a memory or maybe send it out to another peripheral and so on. So that's why data signals are also important, and they are bidirectional, as we have already seen in the previous. And we also have address signals, which are unidirectional because we have to provide the address from the CPU, and memory retrieves this address, or I/O devices retrieve this address, and we get the specific device or specific location in a memory that we can retrieve the data from. And lastly, we have got buffers. Now, buffers together with the converters, we use them to condition the I/O signal levels. So sometimes I/O signal levels are lower. We have to buffer them up so that we have strong enough signals to send it out, or maybe so that the CPU can process it inside. Okay, so this was a typical microcontroller system. Now, we have seen that microcontroller is a simple block over here, but what do we have inside of that? And this is what is all about this course. what do we have inside of that microcontroller, what kind of resources that we have got over there that we can use it to implement any type of system. Because we have to understand the microcontroller, we have to know what we have got on our hands in order to perform specific functions. Okay then, so here we go. This is the inside of the microcontroller unit. The brain, the boss, central processing unit, CPU. We have got the memory, any kind of memory, ROM, RAM, EEPROMs, and so on. I/O data registers, which are interacting with the I/O ports and the outside, and I/O control and status registers. Now, if we explain them one by one, what we have said about the CPU, it controls the operation, and it's the place where the most processing is happening. Then we have got I/O control, status, and data registers. So what was happening over here? We use these registers in order to store the data coming from outside or if we are sending out, okay, with the I/O ports. Then data and programs are stored in the memory blocks, okay, read-only memory. They are permanently stored when they are manufacturers like device IDs, manufacturer ID, and so on. They're all stored over there. EEPROMs and RAMs. RAM is used regularly with the CPU, so it's quick access. EEPROMs, erasable, programmable ROMs, which they are erased by the UV lights, and EEPROMs, electrically erasable, which we can easily reprogram them like we use in today's flashes. Okay, so next thing that we are going to talk about are memories, and this is the computer organization, the microcontroller units, and embedded systems in general, what we have got as logic blocks.